So welcome to this review video for chapter 15 of Beam for electrolyte transport. As you all know, this is an important topic for your exam. So I just wanted to make sure we have a brief video where we go and discuss all the different topics we have learned in this. And hopefully this will help you prepare for the exam. And I'll also point you where to look for different kinds of material in your homework problems, lectures, and so on. Okay, so remember that electrolyte transport deals with movement of ions, which are charged species. So if it is also sodium chloride in water, we make sodium ions and chloride ions. So that's how we kind of define electrolyte transport. So we are talking about ions which are moving with the usual kind of transport equation. So this is what we had. Plus we also had a reaction. So we are ignoring reactions for now. We had something like this in the usual species, but now we have also added another term, ZI F by RT del dot CI grad phi. So this next term, so this was convection, this was diffusion, and now this is a new term which is called electromigration. And this migration essentially happens because ionic species are charged. So for instance, if we have Zi here, chloride, for chloride ions it's -1, sulfate ions it's -2. Then we have calcium ions, it's +2, sodium ions is +1, and so on. This is the valence. Di remains the diffusivity, which was the same. Then we have this F to be the Faraday's constant. R to be the gas constant. And so Faraday's constant is charge carried by 1 mole of electron. So it's 96,500 coulombs per mole. Okay, so coulombs per mole. Gas constant, T is temperature, and then phi is electrical potential. Ci remains the same as the concentration. So we had discussed this, that this is essentially what you get. There is a new part which comes because of electromigration. Another way to write this equation is del Ci by del T plus del dot Ni equal to 0, where Ni now has 3 parts, Ci dot V minus Di grad Ci minus Di Zi F by RT Ci grad phi. Okay, so just wanted to show this form as well if you prefer to just think in terms of fluxes instead of the governing equation. This is the third part, is the electromigrative flux. So if there is no potential gradient, there is no electric field, there is no electromigration flux. So if phi is constant, grad phi is 0, so there is no flux. Zi is 0, if it's neutral, there is no flux, so you need a charge and an electric field and some concentration of the ions. But now we have also added another term in the equation, which is the phi. So we need to close the system of equations, and that's basically the Nernst-Planck equation comes in here. This is the Poisson equation, and these are called the Nernst-Planck equation. Nernst-Planck, and this is called the Poisson equation. And this is summation ZI CIF. Okay. So basically, essentially, you take the full charge per unit volume, and that's how you can essentially get the full equation. Okay, so that's the basic equation, and so these are together called Poisson-Nernst-Planck. And we said if we knew how to solve the full problem, we would, but they're very complicated. So we studied the simplest analysis. First, we said rho E is equal to 0 and 2 ions. So we studied simple when velocity is equal to 0. Velocity equal to 0. Rho E is equal to 0 everywhere. So velocity is equal to 0, rho E is equal to 0. And then we said we only have 2 ions, Z plus minus and D plus minus. And we have a 1D system. In that case, you can transform all the equations written above And you can show that they will simply become del C plus by del T is equal to d effective del square C plus minus by del Z square del X square. And basically it becomes an unsteady equation because both the ions have to like kind of travel together and keep and maintain the same diffusivity, and then d effective is given by Z plus minus Z minus d plus d minus by Z plus d plus minus Z minus D minus. Okay, so you can essentially solve the problem like an unsteady diffusion equation, but you just add this D effective instead of D plus or D minus, because that's the effective diffusivity that you get out of the system. And that happens because an electric field develops it. And so just to make it clear, D effective is between the D minimum and D maximum. So it basically promotes the motion of the slower moving ion and retards the motion of the faster moving ions so that they can stick together and keep an electroneutral system. Okay, so that's the first part. The second part we discussed was I. I was current per unit area. Current per unit area. And this comes out to be summation Zi NIF. And this for Di equal to D. So this is for same diffusivity systems. This essentially all the other two terms in the fluxes, these two terms vanish. And essentially you get Zi F square CID by RT. And this is essentially called the conductivity. Okay, so essentially you can kind of get like conductivity times. So the system looks like a resistance. So its current is proportional to grad minus grad phi, and looks like a resistance. And then we discuss the second case where we have a charged surface. Charged surface. Now we will have no longer, we will still have V equal to 0, but we don't have rho E equal to 0. We don't have the electron neutrality condition valid anymore. And so here you solve the equations. And so if this is a positively charged surface, then negative ions become like this, and positive ions remain look like this. And we had derived, these are called the Poisson-Boltzmann equation. So first you get the Boltzmann distribution for 1:1 electrolyte. You get out that C plus minus is equal to C naught minus plus Fi by RT. And that gives you that epsilon d square phi by dx square. So 2f C naught sinh of Fi by RT. For small potentials, basically we get d square by d phi by x square to phi by lambda square, where lambda is the Debye length. By 2f square C naught. This is the Debye length. So this is what you get out for the small potential limit. For the large potential limit, you did the homework problem. And then importantly, I described here that the result becomes phi is equal to phi d exponential minus x by lambda. And the boundary condition is Qs on charge on the surface, charge density to be more precise, charge per unit area, minus epsilon n dot, where n points into the surface. So this becomes minus epsilon del phi by del x and x is equal to 0. And Qs comes out to be epsilon phi by lambda minus phi d by lambda. Actually plus epsilon phi d by lambda, not minus. The minus gets cancelled because of the derivative. epsilon phi d by lambda, and this is equal to minus q dl. And then we also calculate the capacitance by taking the derivative of qs with the q dqs by d phi d is equal to epsilon by lambda. Now, some important things here to note is that this equation that we had written here, charge here, this could be the mobile charge, but I can have some immobile charges as well, as you have in your homework 5 problem 3. Okay, so practice that. And then this can be spherical geometry. So that is homework 5 for round 3 as well. And then you can have a non-linear system where you can get a different, so that you get a different, not like a exponential decay or something like that. You actually get a more complicated function, and that's homework 5 problem 4. So remember that you can always look them up and kind of learn how to think about these problems in a non-linear perspective. Then finally, the last topic we discussed, what if we add flow? If we add flow to the system, and the problem we mostly discussed was the electroosmosis problem. So here the main thing to remember is now that we have a del dot V equal to 0 minus grad P, and this is a Stokes equation, low Reynolds number equation, plus, and I'm ignoring gravity for now. These are the equations. So these are Stokes. So low RE is assumption, no gravity is the assumption. And this is what the equation you get out for your Navier-Stokes equation, where this extra term is now the body force because of the electric field. So rho E times grad phi, and rho E is written as minus epsilon del square phi using the Poisson equation. So we use this, and the most important part was that if we have an Ex here, and this is positively charged, then I will make a negatively charged layer. And actually, I liked Felipe's explanation quite a lot. He was saying basically, if it's a negatively charged double layer, the liquid in that region will just move opposite to the electric field. So essentially, the charge will just move like if it's the whole of the liquid is negatively charged, so it'll move towards the electric field. And that's called electroosmosis. So you get a flow like this. So the direction is easy to understand, like through this approach, just opposite of electric field. We don't have to think about anything else, just simply remember the charge of the double layer, and that's how it moves. Okay, so this is a simpler way to think about it. We also had the idea that you can think that electric field is happening in this other direction, then I will have a shear force, and that is another way we discussed it in the class. Okay, and recall that far away from the surface, essentially there is no charge density, so there is no electric force, and there is nothing to balance. It's all in the double layers really. Okay, so then we basically what we did here was we argued f of x comma y is phi equilibrium of y minus exx like this. And once you have this phi equilibrium of y minus ex of x, then essentially you could easily show from this equation with the assumptions that we had that it basically becomes a problem. The problem comes out to be epsilon I believe this is what you get out, and then phi equilibrium we know from the other condition that comes out to be zeta exponential minus y by lambda. Okay. So then you kind of can integrate things and get out the velocity for electroosmosis, which is an exponential velocity. So homework 6 problem 5 is a good one. Did I say homework? Everything is homework 6 here. Sorry, I made a mistake. Homework 3 problem 4 and 5, and so that will also help you figure out the electrolysis part, the body force essentially. Okay, this is called the weak field approximation, where we broke the potential into 2 parts. So with that, let me know if you have any questions, and I look forward to seeing you in the exam. Bye bye.